Ta-da. Okay, a little dead air there, but that's okay. Hey, V-boy is a constant.
No, he was the way boys.
It's
I
zero.
tried that. I tried.
So it goes away, right?
No, it goes
No?
away, but it doesn't fix it.
DXT. Yeah, DXT.
What about the XTT?
DXT. Anyways, I need to take derivative of that zero.
Right, that's what I'm saying. Yeah. Anyway, but we digress. Okay, so today we're going to talk about minimizing, maximizing stuff, optimization problems. Take a look at the packet. Whoops, Jeremy, you need one? All right, so we're on 72AB4. Let's see how that works. All right, a man has 340 yards of fencing. Okay, let's go over here. 72AB4. So we have 340 yards of fencing for enclosing two separate fields, one of which is a rectangle twice as long as it is wide, and the other one is a square. Okay, the square field must contain at least 100 square yards, and the rectangular field must contain at least 800 square yards. If x is the width of the rectangle, what's the maximum and minimum values for x? In other words, this is a closed interval problem, and they're not telling you what the interval is, you got to figure it out. So, let's draw this out. We got a rectangular field. And the width is x. Now they're saying the length is twice the width, so 2x. Then there's a square field. I'm not drawing this to scale because I don't know how big the side of this is compared to the side of this, obviously, right? But pretend that's a square. It says that, okay. It says that, what? We have 340 yards of fencing. That's the perimeter, isn't it? But for both. Well, how much have I used up here? Give me the whole perimeter, 6x, right? And I have 340 yards altogether. So, what's left for this? Exactly. So I'm going to write 340 minus 6x, which is how much fencing we have left after we use 6x here. And then we got to divide it by 4 because we have 4 equal sides to fence here, right? So that's what this side is. By the way, that goes in nice. Isn't that 85? I'm going to write 85 minus 3/2 of x. How about we write it that way? So each side of the square is that. So how do you deal with part A? What is the interval for x? Yeah, no problem. What's the smallest value of x? What's the biggest value of x that we can consider in this problem? Well, remember what they said. The square field has at least 100 square yards. Well, how do you get the area of the square field? Side squared. Okay, so 85 minus 3/2 x squared is at least 100. In other words, it's greater than or equal to 100. Okay? What about this one? It says that the rectangular field must hold at least 800 square yards. So what's the area of this thing? 2x squared is at least 800 square yards. So solve for x here, and you'll probably get a domain for x. How would you solve for x here? Okay, so x squared is greater than or equal to 400. So x is greater than or equal to 20. Yeah, I know I'm taking the principal root of 400 because it doesn't really make sense for x to be negative. So I'm talking about plus or minus 20, right? Just plus. Okay, now what? Yes, there you go. Now what? Well, do the same thing. What do we do first here? Nah, too tough. It's already factored. Square root, sure. 85 minus 3/2 x is greater than or equal to 10. So, negative 3/2 x is greater than or equal to negative 75. And if we multiply, well, how do we get rid of this thing? Divide by negative 3/2 or multiply by negative 2/3? What happens when you multiply an inequality by a negative amount? It switches, so we get x is less than or equal to what? Negative 2/3 of this is what? 50, right? A negative times a negative is a positive. A third of 75 is 25 times 2 is 50. So there's your interval. X is between 20 and 50. Right? X is less than or equal to 50 and x is greater than or equal to 20. X is greater than or equal to 20. I just wrote it backwards. All right, now that's interesting because part B says, what's the greatest number of square yards you can enclose in these two fields under these constraints? So you want to maximize the total area enclosed, right? Well, remember the closed interval test. You got to check the endpoints, and you got to check the where you might have a relative min or max, where the derivative is 0, that kind of stuff, right? So let's do that. What is the total area enclosed? 2x squared plus this stuff, right? So let's take the derivative of that and see if it's going to have a relative min or relative max somewhere. So let's go over here. Let's say A, the total area enclosed, is 2x squared plus 85 minus 3 halves x all squared. Okay? Now I want to set the derivative equal to 0, see if it changes sign to positive or negative, get a max, that kind of thing, right? So what's dA dx? 4x plus 2 times 85 minus 3 halves x to the first times negative 3 halves. Fine. Good. All right, let's simplify this a little bit. That's going to be 4x, and then let's see, this 2 and this 2 are going to cancel. Negative 3 times 85 is 3 times 80 is 240, 3 times 5 is 15, so 255, and it's negative, right? So minus 255. And then I got negative 3, remember the 2 canceled. Negative 3 times negative 3 halves is positive 9 halves x. Okay, let's simplify that even more. Isn't this 8 halves combined with 9 halves is 17 halves x. So what do you want to know about this derivative? When it's 0. So when is it? What do you do? Add the 255, okay. And multiply by 2 and divide by 17. Well, if you multiply by 2, you get 510, don't you? If you divide by 17, it goes evenly, doesn't it? How many? 30. Okay, so now, usually what you do with the first derivative test is now you do a sign line and mark 30 as a 0 and see if the derivative is positive before, negative after, so you have a max, or negative before, positive after, so you have a min. You don't have to do that here, though, because it's a closed interval. All you have to do is consider the endpoints, 20, 50, and this critical point, 30, and evaluate the area there and see which is the largest value. You're looking for an absolute max. Okay? So we're going to evaluate this area at these different points. Remember what the area was? This thing. Okay? All right, now I guess, I know we only had bearskins and stone knives in 1972, but let's bring out Hal. What the heck? All right, Hal. Let's see. Let's go into y equals. I'm going to plug in the area here. 2x squared, just for fun. All right, so that's the area of what? The rectangle. Plus quantity, 85 minus 3x over 2, wasn't it? All squared. There it is. And I'm just putting that in there. That's what it was, right? Yeah. I'm just putting that in there so I can evaluate it on the home screen. So what's y1 of 20? Okay. What's y1 of 30? And what's y1 of, what, 50? So do you see an absolute max? What's the max? 5,100 square yards. When does it occur? When x is 50. Okay, so let's say so. This gave us 3,825 square yards. This gave us 3,400 square yards. Wait, am I remembering this right? 38, yeah, and this gave us 5,100 square yards. So what's the answer? A max is 5,100 square yards, occurs at x equals 50, yards. Okay, what does that mean? Well, that means that the rectangle was 50 by 100, right? Because that was x, that was 2x. And the square was 85 minus 3 halves x. Well, 3 halves of this is what? I'm not hearing it, what? 75? So it's 85 minus 75 is 10. All right, so this area is 5,000, and this area is 100. That's the 5100. Okay? Any questions how any of that makes sense? Now, you could also do the closed interval test on the graph. If I graph this thing on the closed interval from 20 to 50, whoops, you should be able to see where the absolute max is. So I'm going to change my window to include only 20 to 50. And it's not going to be a square window or a friendly window, but there it is. Are you serious? Really? Okay.
As soon as you can.
Yeah, next period, yes.
It's going to cost.
Yeah. Yeah, sure. Okay, so there you go. And then we already know that the y values are not negative, so might as well make this 0. And they get sort of big, so I don't know, maybe 6,000 and 1,000. And let's see what that looks like. So that's the 3825. That's the 3400. And look how you get, even though that's a relative, that's a critical point, the max occurs at an endpoint. That's the 5100. All right, if you trace it out, you'll get all of that. Let's see, what if we do that? Go to F5, value at 20. You're going to get the 3825, right? And at 30, you're going to get the 3400. And at 50, you're going to get the absolute max. And by the way, this is a relative min anyhow, so that wouldn't help. Right? Questions? The window? Yeah. I just made it big enough to include the numbers we're playing with. Since we already had the answer, that was sort of easy. Usually it's the other way around. If you're using the calculator, you don't have the answer yet. You got to play with the window a little bit. All right, now today's optimization, right? Now, you notice that you have 10 free response questions in this packet. We're not going to finish this today, obviously. We're going to finish this Tuesday and Wednesday, and we're going over multiple choice test. We're getting it back on Monday. So bring this back on Tuesday and Wednesday. But today we're going to focus on those questions that are labeled opt. Do you see at the top of the first page it says opt, optimization? Go to the 6th page, I think it is the next one. 73AB6. Okay, you got that one? I labeled it opt also, so it's easy to find. So I'm going to skip the other ones until Tuesday. Okay, so here's another optimization question, which may or may not involve the first derivative test, or the closed interval test, or even the second derivative test, who knows? All right, so 73AB6 says, a manufacturer finds it costs him x squared plus 5x plus $7 to produce x tons of an item. At production levels of 3 tons, he must hire additional workers, so his costs increase by 3 times x minus $3 on his total production. If the price he receives is $13 per ton, regardless of how much he manufactures, and that his plant capacity is only up to 10 tons, I guess per day, what level of output will maximize his profit? So we have to figure out the cost function. We have to figure out the we have to figure out the revenue function. We have to figure out the cost function, and we have to figure out the difference, which is the profit function. Right? Okay, let's do it. Alrighty. So this is 73 AB6. Notice it's a piecewise defined function. Your costs as a function of x are x squared plus 5x plus 7 at production levels below 3 tons. X is the tonnage of production. C is the cost in dollars. Okay? Question? Yeah? Oh, okay. So the other one starts at 3. Okay, fine. We'll include 3 here and not include it here. Sounds good. Then it says it costs more at production levels over 3, right? So that would be adding 3 times x minus 3. Well, what's 3 times x minus 3? Distribute that. 3x minus 9. And I'm going to add that to my cost function. So just added 3x and negative 9, right? And this is for production levels between 3 and 10, but not including 3. Not including 3. Yeah, do what you say what you do. Okay. And I guess you're allowed to go up to 10. Okay, so technically, what's the minimum you're going to make? 0. So this is a closed interval from 0 to 3. This is a closed interval from 3 to 10. Okay. So what's the profit function? I want to maximize the profit, so I need to take the derivative of the profit function. So how do I get the profit function? Well, it says you make $13 per ton. So what's your profit? Or what's your revenue? Let's make it easy. How much money do you make? 13x. So what's your profit? 13x minus this stuff. Okay, so here's your profit function. 13x minus this. Let's say we're going to... Okay, so 13x minus that is what? It's 8x, right? Okay? So all I did was I subtracted this from 13x. So that becomes negative, that becomes negative, 13 minus 3 is 8. And same thing here. All right, 13x minus 8x is 5x, and then subtract x squared from nothing, it becomes negative, and subtract negative 2 from nothing, it becomes positive. Same domain. So, now we need the derivative, don't we? We need to know if there are any critical points on this domain. If this derivative attains a 0 in here, we have to consider it. If the derivative of this attains a 0 on this domain, we have to consider it. We also have to consider the endpoints, 0 and 10, yeah. Minus 7, okay, because the profit is 13x, how much money you make, minus the cost. No, because it was 13x minus 5x, right? So this becomes negative, because I'm not subtracting x squared from anything. And this becomes negative, right? But this is 5 from 13, it's just 8, so we're good, okay? All right, so what's the derivative? What's p prime? Well, go ahead, differentiate and you get negative 2x, let's bring it up, negative 2x plus 8, and this one, negative 2x plus 5. There you go. Alrighty, so, why did I omit this equals here? We used to have an equals here in P. Why is it gone? Because the derivative may not exist at 3. I don't know. Look at this thing. This thing is continuous at 3. What if you plug in 3 here? You get negative 9 minus 7 is negative 16 plus 24 is 8, right? What if you plug in 3 here? You get negative 9 plus 2 is negative 7 plus 15 is 8. So it's continuous. Right? This goes through the point 38, this goes through the point 38. So, right? Both branches touch. So it's continuous, but is it differentiable? No. Look, what if you plug in 3 here? You get 2, right? What if you plug in 3 here? You get, what? You get negative 1, right? So it's not differentiable. I can't say that the derivative exists at 3, because it doesn't. What kind of curve is that? Is that a cusp, a corner, a vertical asymptote, a hole? What is it? Probably a corner, yeah, because yeah, the derivative exists on both sides, but they're not the same, so it comes together at a corner. It's not a cusp, because that's if the derivative is undefined on one side that goes to infinity or something. All right, so now what do we usually do with the derivative? We set it equal to 0 and see if there's a critical point. Well, when is this 0? At 4, right? Is that on this domain? No, so we need not consider it. What's the zero of this? 2, 5 halves, positive 5 halves, isn't it? Right, because we said it equals 0, you subtract 5, negative 5 over negative 2 is 5 halves, 2.5. Is 2.5 in here? No. So this didn't give me any more information. Okay? But I know the derivative doesn't exist at 3. Remember, critical point is where the derivative is undefined too, not just where it's 0. So this 0 didn't help, it wasn't in here. This 0 didn't help, it wasn't in here. But this, where we have a corner, it's undefined, we have to worry about that. The derivative can change sign there, we could have a min or a max on P. Okay, so it's time for the closed interval test. Here we go. Closed interval test says, evaluate P at the endpoints, which was, it went from 0 units of production to 10. Hopefully you don't get a maximum here, that would make no sense. And what else? At 3, because that's where the derivative is undefined, so you could also get a max there. The critical points are where the derivative is 0, and the supercritical points are where the derivative is undefined. All right, so let's plug this in, yeah. No, I'm trying to maximize P. Okay, so I'm trying to find an absolute max for P, just like last time. We did the same thing for A, for the area, right? All right, so let's plug that in. Now, we're going to plug in 0, 3, and 10, huh? Okay, let's go back to our P. If I plug in 0, I plug in 0 here, right? So what do you get? Negative 7? Okay, let's put that on our table. Negative 7. Well, hopefully that's not the maximum profit. Your business is not a very healthy business. Okay. Then it says put in 3, and then we say this includes 3, right? Not this. But by the way, it was continuous. We plugged in 3 before, and what did we get? Did we plug in 3 before to see if it was continuous, and we got both sides gave 8. Right, okay, so let's say that's 8. Okay, $8 per day. Maybe the units are up like $8,000, so whatever it is. And plug in 10. Now 10 you can't plug in here, right? Over here. So plug in 10, and you get 52 minus 100 is negative 48. Hopefully that's not your max profit either. So there you go. Absolute max profit. Okay? All right, so, or you can say, therefore, P max, or the absolute max of P, is $8. Are you serious? Well, it's $8. I don't know what that means. It might, it might be for like 8 million. I don't know what the hell it is. And it occurs at X equals 3 tons of production. Okay, so in other words, did he have to hire anybody? No, because 3 tons of production doesn't include the new help, right? So this isn't happening, this isn't happening. And this isn't happening. Right? It's just the first branch of P that we're interested in. Okay, questions about that? We did find P prime. We didn't write it down, but we talked about it. We said that P prime is this, and the 0 of this is 4, but that doesn't make sense. 4 doesn't help. It's not in here. This parabola has a min or max, a critical point at 4 because of this. But this parabola exists for all x, but the problem only exists from 0 to 3. This is part of our problem only from 0 to 3. So in the context of the problem, the 0 being at 4 doesn't help. And the same thing here. This 0 is at 2.5. So that doesn't help either. All right, so we did discuss that. We do need to figure out when P prime is 0, but it didn't help. All righty. Any questions on that? So far we're doing first derivatives where there's 0 and closed intervals. Check the endpoints. That's all we're doing, right? All right, take a look at the next one unless there's a question. Any more questions? We good? Okay. Go to 82AB6, the next one that's labeled opt at the top. 82AB6. Okay. It says a tank with a rectangular base and rectangular sides is to be open at the top. It is to be constructed so that its width is 4 meters and its volume is 36 cubic meters. if building the tank costs $10 per square meter for the base and $5 per square meter for the sides, what's the cost of the least expensive tank that you can build under these constraints? All right, well, let's, why don't we draw this crazy thing? So I'm going to get some straight lines here. It's a tank, right? Sort of. Well, pretend it connects, okay? Something like this, okay? Got a little foo art there, but there you go. Not quite, but oh, come on, it's got to be perfect. Ah! Ta-da! See, you didn't see that. I didn't mess up at all. All right, so this thing has, all right, so it's a box, right? And, well, you know what? Wait, just for fun. Just for fun. Ignore the arrows. All right, so there you go. So this is a box. It has a length and a width and a height, right? So the length, the width, and the height. Okay? So, now, what do they tell you? They tell you that the width is 4. That's a constant. That's not going to change. So width has to be 4 for some reason. But you can play with the length and the height to minimize the cost of building this fish tank, or whatever it is, right? They also tell you that the volume is a constant 36. And how do you get the volume of a box? Right, so that's length times width times height is 4 times L times H, isn't it? 4 times L, I'm doing it in a different order, but same thing, right? Okay, good. Now, okay, remember the top, there is no top, right? The bottom, what's the area of the bottom? It's 4L. Okay, so let's talk about the area, the surface area. It's 4L. Okay, now, but the bottom costs $10 per square meter. Is that right? The bottom, the base? Right. So, you know what? Let's go straight to the cost function. Right, so the cost is the area times 10 is 40L. Is that okay? Okay. Now let's do the sides. We did the bottom. The top, there is no top. The bottom, we did it. That's $10 per square meter. All right. The sides, the 4 sides now are $5 per square meter. What's the area of this side? 4L. What's the area of that side? Sorry, not 4L, 4H. And what's the area of this side? 4H. So the two together is 8H times $5 per square meter, 40H. So far so good? How about the front face? What's the area of the front? The length times the height. And how about the back? Length times the height. So that's how much for front and back? 2HL. And we're multiplying that by $5 per square meter? So 10HL. Okay, there's your cost function. But notice there's a constant width and a constant volume, so there's a relationship between L and the H. So, can I get rid of H if I wanted to, for example? See, if I could get rid of L and differentiate with respect to H. I could get rid of H and differentiate with respect to L to minimize the cost, right? All right, so say I want to get rid of H. What's H according to this? Can you get H alone just looking at this? H is what? 9 over L? Perfect, good. So whenever I see H, I'm going to put in 9 over L. Okay? So 40L plus 40 times 9 over L. That's an L. Plus 10 times 9 over L times L. All right, just replace this H and this H, that's all. All All right, well, what happens here, this, you just multiply it, right, this over 1, so you get the cost function. This is a cost as a function of L and H, right? This is going to be the cost function as a function of L. This is L, damn it. Keeps on looking like an E. Okay, so this is 40L. What's this? 300 plus 360 over L, good. And what happens with the L's? So what do you get? 90. And if we want to minimize the cost, what are you going to do? Well, that's the cost. What am I setting equal to 0? The derivative. Let's find the CDL. What is it? Okay. Minus. So 360 over L squared. Think of this as L to the negative 1. So the negative 1 goes in front, and you get L to the negative 2. And you can write it that way, but I feel like writing it this way. And what about this piece? That zeroes out. Okay. So now we want to set this equal to 0 and see if we can get a min or a max out of this, right? Well, actually, they're looking for a min. So let's do it. How do you solve this? Subtract 40? You could, but I'm going to add, because I feel like it. Then what? Right, cross multiply, right? Then what? All right, and L squared then is 9. And so L is technically plus or minus 3, but that's not in the domain of the problem, so I can ignore the negative 3, right? A length can't be negative. Okay, so my critical point is L is 3 meters. What do you do with that information? Are you done? That's the min. I'm done. No, that's a critical point where the min might exist. That's where it might exist. So first, I got to figure out if it really is a min, and second, I got to figure out what the minimum number of dollars is, right? I'm still missing 2 pieces of information. So I have to do a sign line on this derivative. Let's do a sign line. Oops. Okay. So the smallest that L can be is 0, right? You're not going to have negative L's to this L. And this is the CDL, which has a 0 at 3. Inclusive of what? Well, technically, if L is 0, I made it inclusive. You're saying don't make it inclusive? Technically, no, it's not, because if L is 0, you don't have a box, right? So, yeah, I guess you should make it an open interval here. Remember, on the AP, they really don't worry about that kind of stuff. They worry that you stop at 0, but they don't worry about whether you close it or not. Okay. Now, technically, L could be infinite, I suppose. If L is infinite, well, not infinite, but if L gets really, really, really humongous, then H just gets really, really, really small, right? Now, L can never be infinity, right? And H is never going to be 0. So saying that that's the domain makes sense. It can go as big as it wants, except it's not infinite. All right, so what do I want to do? I want to evaluate C prime, what you usually call C prime, right? Before 3 and after 3. Well, what is it? It was this. So say I plug in something between 0 and 3, like, I don't know, 1. That's negative. And what if I pick something bigger than 3, like, I don't know, 9? Is 9 a good one? 6. It's positive, right? 6 is easy, because 6 squared is 36, into 360 is 10, 40 minus 10 is positive, right? 1 is easy, because 1 squared is 1, 360 over 1 is 360, 40 minus 360 is negative. So let's say that. That's negative, that's positive, so C is decreasing, then it's increasing. Therefore, C min equals C of 3 equals what? What is C of 3? Where's C? Now this is C is a function of L, this one. So plug in 3, what do you got? Wait, what for this? Just plug in 3 here. 3 for L, what do you get? 120, 3 here. 120, so 120 plus 120. 240 plus 90. 330, yeah. Is 300, whoops. It's 330 bucks. and 3 is in meters, right? There you go. Now, I'm saving time here because we're running out of time, but this really, they're really being a pain about this. The AP readers every year now, they're getting more and more of a pain about this. Writing that is not enough, and writing that is not enough. They want you to write this in words, okay? So just say a sentence for this. They want you to describe this in words, okay? The maximum cost of the tank is $330 because L equals 3 is 3 meters gives you a critical point whereby the derivative is negative before and positive after, so the function's decreasing, then it's increasing. They actually want you to verbalize this entire thing. Okay, this is your work, but you got to write it all out in words. They're a pain in the ass about this. People are not getting full credit on questions like this, stopping here. Okay? All right, that's good for today. Thanks for watching. Bye.